Hello everyone, my name is Zarina from Alatu International University in Bishkek. I'm here today to present our work on a new method for classifying epileptic seizures using EEG signals. In simple terms, we developed a smart system that can automatically identify different types of seizures from brainwave recordings, and we achieved very high accuracy, over 98%. Epilepsy is one of the most common neurological disorders in the world. It affects approximately 50 million people globally. That's about the population of a large country. The main tool doctors use to diagnose epilepsy is EEG, which records electrical activity from the brain using electrodes placed on the scalp. But here's the challenge. Analyzing these recordings manually takes a lot of time and requires highly trained specialists. This means patients often wait too long for diagnosis. In recent years, researchers have started using machine learning to automatically analyze EEG signals. This is great, but there's a big problem. Most existing models treat all EEG channels equally. However, we know from neuroscience that different types of seizures affect different parts of the brain. For example, focal seizures start in one specific area, while generalized seizures involve the entire brain. This is the key insight behind our work. What if we could teach the model to automatically focus on the most important channels for each type of seizure? This is exactly what our method does. Before I explain our method, let me briefly talk about what other researchers have done and why our approach is different. There are two main families of methods used for EEG classification today. First, traditional machine learning methods like support vector machines and random forests. These work well with structured data, but they treat all features equally. They don't learn which EEG channels are more important for specific seizure types. Second, deep learning methods like convolutional neural networks and attention mechanisms. These can learn feature importance, but they need huge amounts of data, often millions of samples, and they require powerful computers and long training times. Our approach fills the gap. We combine the best of both worlds. We use tree-based ensemble learning, which is fast and works with limited data, but we add a mechanism to learn channel importance. This makes our method both effective and practical. So, let me now explain exactly how our adaptive channel weighting forest works. Let me now describe the data we used in our experiments. We used a publicly available dataset called the Bangalore EEG Epilepsy Dataset, or BEAT for short. This dataset contains 8,000 samples, and each sample has 16 features derived from EEG recordings. The dataset has 4 classes, and importantly, it's perfectly balanced. Each class has exactly 2,000 samples. The classes are Class 0, healthy subjects with no seizure activity. Class 1, generalized seizures, where the entire brain is affected. Class 2, focal seizures, which start in a specific brain region. Class 3, seizure events, which is a broader category. For our experiments, we split the data into 80% for training and 20% for testing. So we trained our models on 6,400 samples and tested on 1,600 samples. Before training, we standardized all features so they have zero mean and unit variance. This is a standard preprocessing step that helps machine learning models perform better. Now, let me explain our algorithm in detail. Now, this is the most important part of our presentation, the core algorithm we developed. The main idea behind ACWF is very simple. We want the model to learn which EEG channels are most useful for classification. Think of it like this. If a doctor is looking at an EEG, some electrodes provide more useful information than others depending on the type of seizure. The model learns this automatically. Here's how it works. We built a forest of decision trees, 800 trees in total, but unlike a standard random forest where all features are treated equally, we maintain a weight vector that tells us how important each channel is. After each tree is built, we update these weights using 3 mechanisms. First, we use stratified bootstrap sampling. This means when we create training samples for each tree, we make sure each class is equally represented. This prevents the model from being biased toward the majority class. Second, we measure how important each channel is using something called permutation importance. The idea is simple. We temporarily scramble the values of one channel and see how much the accuracy drops. If accuracy drops a lot, that channel is important. If it doesn't drop much, the channel is less important. We also smooth these importance values using exponential moving averaging to reduce noise. Third, we update the channel weights using momentum, which helps the model learn faster and more smoothly. We also apply L1 regularization, which encourages the weights to become sparse, meaning only the most important channels get high weights, and the rest become very small or zero. After each update, we make sure all weights sum to 1 by projecting them onto what's called the probability simplex. Let me now show you the mathematics behind this. Let me walk you through the mathematics behind ACWF. I'll keep it simple. Formula 1. Permutation importance. This formula calculates how important each channel is. We look at the accuracy on out-of-bag samples. These are samples that weren't used to train the current tree. Then we scramble the values of channel J and see how much accuracy drops. If the drop is large, that channel is important. If there's no drop, the channel is not useful. Formula 2. EMS smoothing. The importance values from individual trees can be noisy, especially early in training when the forest is small. So we apply exponential moving averaging. The parameter alpha controls how much smoothing we apply. With alpha equals 0.3, we give more weight to recent estimates, but still keep some memory of the past. Formula 3. Momentum update. This is where the weights are actually updated. We maintain a velocity vector v that accumulates momentum. This helps the weights move in a consistent direction, making learning faster and more stable. The learning rate in HAT-T decays over time, so we make smaller updates as training progresses. We also subtract a small L1 regularization term lambda to encourage sparsity. Finally, we project the weights onto the simplex, meaning they sum to 1 and are all non-negative. Formula 4. Final prediction. For a new input, we multiply it by the learned weights, then pass it through all 800 trees. Each tree gives us a probability for each class. We average these probabilities and choose the class with the highest average. The key parameters we used are alpha equals 0.3 for smoothing, mu equals 0.95 for momentum, lambda equals 0.002 for regularization, and t equals 800 trees. Now let me show you how we combined ACWF with other models to achieve even better performance. While ACWF works well on its own, we wanted to push performance even further. So we combined ACWF with 5 other strong models to create a heterogeneous ensemble. The 6 models we used are our ACWF with 800 trees, tuned XGBoost, tuned random forest with 500 trees, SVM with an RBF kernel, light GBM, and CatBoost. The blending formula is simple. The final prediction is a weighted sum of each model's probability predictions. We optimize these blending weights using a 500 iteration random search with a Dirichlet distribution. The optimal weights are shown here. Light GBM got the highest weight at 0.687, followed by CatBoost at 0.095, XGBoost at 0.087, Random Forest at 0.059, and SVM 0.053. Now, you might notice that ACWF has the lowest weight at only 0.019, but here's the key point. ACWF brings diversity. Its predictions are different from the other models because it uses adaptive channel weighting. Even with a small weight, it significantly improves the ensemble's accuracy. This is a classic example of why diversity matters more than individual performance in ensemble learning. Now let me show you our results. Now let's look at our results. This table shows the performance of all models we tested. The ACWF ensemble achieves the best results across all metrics: 98.06% accuracy, 98.08% precision, 98.06% recall, and 98.07% F1 score. Light GBM comes second with 97.94% accuracy, followed by XGBoost at 97.62%, CatBoost at 97.00%, Random Forest at 96.81%, and our standalone ACWF at 95.13%. This is an important observation. Standalone ACWF performs well at 95.13%, but it's not the best individual model. However, when we combine it with the other models, the ensemble surpasses all of them. This confirms that ACWF's diversity, its unique way of weighting channels, provides complementary information that improves the overall system. We successfully achieved our target of 98% accuracy, which is state-of-the-art on the BIT dataset. Let me show you the per-class performance. Let me show you the per-class performance and the interpretability of our method. This table shows precision, recall, and F1 score for each class. Class 0, healthy subjects, achieves near-perfect performance with F1 of 0.9987. This means our model almost never misclassifies a healthy person as having a seizure, which is crucial for avoiding false alarms in clinical settings. Class 1, generalized seizures, performs very well with F1 of 0.9816. The model can reliably detect these full brain seizures. Class 2 and Class 3 focal and seizure events have slightly lower F1 scores at 0.9687 and 0.9699. This is expected because these two classes are clinically similar and share many EEG patterns, making them harder to distinguish. Now, the second part, interpretability. One of the key advantages of ACWF is that it's not just a black box. The learned channel weights tell us which brain regions our model finds most important. The weights are sparse thanks to L1 regularization, meaning only a handful of channels get high weights. The highest weights correspond to frontal and temporal EEG regions. This makes clinical sense because these regions are known to be involved in both focal and generalized epilepsy. This interpretability is valuable for doctors. Instead of running complex post-hoc analysis, they can simply look at the learned weights to see where the model is looking in the brain. This could help identify seizure foci and guide treatment decisions. Now let me conclude. Let me summarize what we've accomplished. First, we proposed ACWF, a novel ensemble method that learns which EEG channels are most important for classifying different types of seizures. Second, standalone ACWF achieves 95.13% accuracy and provides interpretable channel weights that make clinical sense. Third, when we combine ACWF with 5 other models, we achieve 98.06% accuracy, which is state-of-the-art on the BED dataset. We've successfully hit our 98% target. Fourth, our per-class analysis shows near-perfect classification for healthy subjects and strong performance for generalized seizures. The main challenge is distinguishing focal seizures from seizure events, which is clinically expected. Finally, the learned weights are interpretable, highlighting frontal and temporal brain regions, exactly where neurologists would expect seizure activity. Looking forward, there are several directions we want to explore. First, allowing each tree to maintain its own weight vector instead of a global one. This could capture more diverse feature interactions. Second, scaling our method to high-density EEG systems with 64 to 256 channels. Third, integrating ACWF with deep learning to work directly from raw EEG signals, eliminating the need for manual feature engineering. Fourth, adapting ACWF for real-time bedside seizure monitoring. Fifth, learning separate weight vectors for each class to better separate clinically similar seizure types. Thank you for your attention.